Thanks everybody for attending today. Thanks Patricia for the introduction and welcome everybody. And I also want to say thanks to Pau, our CTO, which will help me answer any questions you might have during the webinar today. Just a few words about Vortex for those of you that do not know much about us. We are a private-owned company that was established back in 2005, and we do not depend on third parties such as investment funds and stuff like that. So all decisions are taken in our headquarters in Barcelona, though we also have offices here in Austin, Texas, to assist in North American countries, and also offices in India and Brussels and China. We're not consultants. This is very important. We do not do any site assessment or similar. We just supply modeled wind data to our customers. Some of them are consultants, so we cannot compete against them, right? Anywhere in the world, both for onshore and offshore sites. And we do not sell any software license. In fact, our data can be used as input for most common resource assessment softwares out there, such as OpenWind, WindPro, and WindSim. Okay. Vortex has focused historically on hindcast kind of solutions for wind energy, but our family is growing. So you can see now here we have two new babies, two spin-offs to work also on forecast solutions for the short term, which is zero energy, and the long term, which is climate scale. And we will soon release a seasonal solution for the midterm forecasting, so please stay tuned for that, right? We offer a bunch of solutions for all stages of wind farm development, and we do that through a very straightforward interface for our customers, but also for people that are not our customers yet. So if you don't, any of you are still not registered, I encourage you to set up a user account where you have access to a bunch of free data. Do not need to do it right now. You can proceed when the webinar is over, right? Once you set up an account, you will also be able to purchase all of our products. But before that, you can download data from the free samples of each product and check how useful they are for your projects. Let's go about to talk about the Vortex offshore experience. And we would like to start by looking at these figures. They're 2020, but we have some updates in 2021, which we can see that China has overpassed Europe in this ranking. And according to these figures, Chinese offshore current capacity seems to be close to 26 gigawatts, whereas US still we just have 2 operating offshore wind farms for the total of 42 megawatt installed capacity. So there's still a long way to go. And if we go through the Global Wind Energy Council figures, it seems that within the next decade, the future looks bright ahead, doesn't it? So the only thing that looks a bit weird to me is that European offshore capacity will grow faster than any other region in the world. But anyway, we'll see. Here we would like to raise up the question number 1. So Patricia, please proceed. Because we would like to know in what countries, in what areas in the world you are developing offshore wind farms. So as you can see this menu, you can start answering. And I guess most of they are here in the US, maybe a few in Canada, maybe Mexico is now struggling with new projects in onshore, so maybe too early for offshore. Let's see your answers that we will show the full results before the Q&A. Okay. Let's go next slide. Let's see if I can. Okay. Vortex, we have basically supplied data for most of the offshore projects worldwide. And this is basically in Europe, but also US, China, and India. The thing with offshore products is that, as you know, there are less measurements available since the metmast or floating LiDARs deployment are both a high investment and not many companies can afford that. And the environment is also different compared to onshore sites due to the topography, and waves are also part of the game. Excuse me, there's something. Excuse me sorry about that. Some issues with my presentation waves. There we are. Let me tell you that at Vortex, we do not currently use a wave model in our offshore solutions. And as you may know, wind generates surfing waves that then change the atmospheric conditions in the site. So it's pretty much challenging. And there are some wave modeling companies out there. So most of them, in fact, they're also Vortex wind data users. So Vortex, we focus on our core business, which is providing model wind data, but we strongly encourage you to add wave modeling for your site assessment in offshore. That's a fact. Okay. Let's talk about the WRF model. So this is what we use. The WRF model is a state-of-the-art of the numerical weather prediction models. This is powered by NCAR. It's an open source tool used by many companies out there, research institutions, and a large community of developers all around the world. And Vortex, we are part of this community. And these numerical weather prediction models are computer programs that solve the nonlinear equations that describe the atmosphere by means of mathematical methods and approximations that can be used to look ahead. So it's the weather forecast we see each day on TV, or looking backwards, which is called hindcast, and you know about local conditions, in our case, the wind anywhere in the world. We also use topography, the land cover, and the reanalysis data sets as WRF input data. And then we downscale by means of nested domains from low resolution grids, because 25, it's taking some time. It's 25, the reanalysis is not good enough to take decisions on wind farm development. So we downscale and we can come up having just high resolutions, which this can be 1 kilometer or even 100 meters. Long story short, this is a picture of what we think is the scenario of real measurements, the modeled solutions, the tools that we use, and our people that are the ones that are skilled in modeling the atmosphere. We have another question here, because we would like to know about the reanalysis, which is the most reanalysis data source that you're using. If it is ERA5, Temera2, or CFSR, obviously, depending on the site, it's also an option for you to answer, okay? Give you a few seconds to answer this second question today. And we can go now for the Vortex solutions. Let's see. Okay. I'm so sorry. I don't know why my slides are not. Sorry about that. Let's see if I can fix it. Let's see if I can. I will have to stop, maybe stop sharing and start again, because for any reason, I don't know what's going on here. Now, here we are. So sorry about that. So our project, it's very important, a message that is that all our products, they start from scratch. So we do not have any data pre-computed. This is important. And so we make sure that the latest reanalysis data sets are used for any of the runs of our customers. So let's go for the first product is our time series. That is what put us on the wind energy map about 15 years ago. These are used when wind measurements are available, but maybe just a few months of data. So long-term extrapolations are needed. This is computed with WRF at 3 kilometers horizontal resolution. It's an hourly timestamp, and we can pull out data from the last 10 years up to the last 38 years, right? The 3 reanalysis data sets available, and series can be calibrated when there are on-site measurements. In August last year, MetOceanWorks validated this solution for 13 offshore sites, comparing that to raw ERA5 data. And if you go to this link here, you can get this more than 150 pages document in our knowledge center. Here you can see all the sites that were validated. 3 of them are in the East Coast in the US. Also, you can see the time period and the different height ranges that were validated. A few takeaways are basically that both for high and low heights, Vortex time series perform better than Rover 5. As you can see here for bias and the root mean square metrics. Even low height figures are slightly better than high ones. And for high wind speeds, our series underpredict in the range of 1.5 to meters per second, whereas Era 5 data goes up to 5 meters per second. But as I said before, you can go through these in much more data and statistics when you download the full document, okay? Next solution, that's FARM. We could say this is our second bestseller product. It's actually used when the wind farm area is already selected for site assessment and energy yield estimation. It's computed with WRF, high resolution maps, 100 meters horizontal resolution. We have 2 sizes, standard ones up to 500 square kilometers and large, which goes up to 2000 square kilometers. The basic outputs are WRG and WRB files, and it can also be calibrated, or what we call remodeled, with on-site measurements. The thing is that with FARM, you don't have time-dependent information. So last year, we released blocks, which can be seen like a step forward of FARM for a more detailed site assessment. Basically, same outputs with some extra features like, let's say, the wind rows for 24 or 36 sectors and other data mainly for stability conditions. But very important, this is time-dependent information. So it's 30 minutes time series at each grid point. So many post-processing data filtering options for the better seasonality analysis. And this is, for example, WRG, WRB files for day to night, winter, summer, and so on. And long story short, FARM plus series, we end up having the blocks. Then here, we are often asked about an area to be included when submitting a FARM or a blocks run in our interface. Here we have the V defined as the area of interest for developing an offshore project. And the question is that, since this is pretty close to the land, do I have to extend the domain, including the area A, to ensure an optimized modeling? That's a question. So when I submit the run, just the V area, or should I go and extend it? And the question is that there's no need to do that. And the reason is that when we set up the WRF model, we include the much larger area than V in this case. So you can feel confident that area A will be taken into account, although we will deliver just the WRG files and all data for your area of interest. As I explained before, we downscaled with nested domains to fully capture the atmospheric condition in your area of interest. And now, next question arises, because we would like to know about your offshore wind projects and how large they are. So if you are developing offshore projects in less than 1,000 square kilometers, between 1,000 and 1,500, up to 2,000 square kilometers, or even more than that. So please feel free to select your answer to this question. That's the last one, and we will see the full results at the end of the presentation before the Q&A. Let's see if I can move forward. It looks like when we pull out an answer, a question, that's when struggles with presentation. Let's see if I can restart again, share screen. There we are. So next product is the LES, which is 1 year of 10 minutes time series. It can be either a natural year or long-term representative. The Vortex, we were pioneers in commercial use for the wind industry back in 2016. And this is a microscale product where data is computed at 4 Hz which means 4 samples per second, and then aggregate it into 10-minute values using Vortex LES, which is a CFD, the computational fluid dynamics algorithm based on large eddy simulations to solve the turbulent eddies, not just parameterize them like standard mesoscale work does, right? And LES is basically for the detailed ambient turbulence analysis, since it outputs the standard deviation data for both wind speed and direction. It is useful when no measurements are available or reliable to characterize the mean flow and turbulence intensity in future wind farms for site assessment, or operational wind farms for load assessment and lifetime extension programs. It can also be used to decide where to install a met mast in a site. Vortex LES is the closest thing to real measurements, since the data format is basically the same that you would get out of a data logger, but you can also have data up to 300 meters or higher and covering all rotor swept area. So even when specific hop heights are required, like 103, we can pull out on demand and we do not charge any additional cost. All Vortex data with LES and all our solutions include all height for the price. One more thing about LES, we could think it's a virtual met mast or LiDAR, a reach turbine position in a wind farm, and it could help to identify potential turbulence issues or underperformance in operating wind turbines. But let's first take into account that turbulence is an historical issue in wind energy. So it can be basically mechanical due to the terrain roughness and the wind flow around objects like mountains, hills, trees, or turbulence can be the ambient turbulence. It can be caused by the warm air rising up, essentially rising thermals of air generated by surface heating, right? This is the one that Vortex can help you through. And when a year of measurements available, the approach could be as follows, just some examples. That would be, for example, getting an LES at met mast or LiDAR position for the same natural 1-year period of measurements. Then you can compare the real data against the model. So it's kind of like calibrating the LES. And then if correlation is good enough, you can, the criteria of what is good enough, it's on your side. It's not on our side to decide, right? But then if it's good enough, you can establish or set up some kind of a transfer function that then you could apply to those turbine positions that have any issues or are underperforming, right? Then you correct the data and you end up having some model turbulence intensity and analyze the data and then conclude if there's an ambient turbulence issue, okay? The question is, what if no measurements available? Then the approach could be pretty much the same. So getting the Vortex LES, but not for a natural year, for the long-term representative at turbine positions that potentially are underperforming, but then model turbulence intensity data is obtained, but not calibrated with measurements. Is this a good solution? Maybe it is not, but it's better than nothing. So for a few $100 at least, you have some information that could be useful, okay? We have many validations for LES. All of them are internal validations. Again, can be downloaded if you go and access your user account or go to our knowledge center. In fact, we have a 18 offshore site validation document. These are the sites. Unfortunately, only 5 of those we got information about the standard deviation, so we could validate the turbulence. This pretends to be a dynamic document, so if we ever have access to new data sets that allow us to validate the turbulence, we will gladly do that for sure, right? And if you see, there are 2 of the sites that are in the US. Also, extremes, another product that could be of your interest, is useful when you need data on extreme wind speed events, right? This is also a microscale product computed with Vortex LES that outputs a 10 minutes time series of 6 complete days per year. So we select the maximum wind speed registered for the last 30 years, and we end up having 180 days time series, right? The same kind of data like LES is included, but we add hurricane and typhoon reporting based on storm track data available, just to make things easier for our customers. And if you have measurements, then we can also provide an additional 180 days of 10 minutes time series calibrated with measurements. Let's go to the customized solutions. But I would say that for a better assistance, the very first thing you can do is contact us and explain about your projects and what kind of data you're searching for. That's it. These are two solutions that you may be interested in, which are offshore wake maps and low resolution grids. Let's start with the first one. So offshore wakes grid maps. The wakes in the wind farms is something that, as far as we are aware of, still does not have an optimized solution out there, right? There's still a long way to go and a lot of R&D work to be done. One of the worst options is what is called the FEED scheme, that includes the subgrid effects of specified turbines in both wind and turbulent kinetic energy fields. However, this parameterization does not consider the rotation of the rotor blades. Maybe a CFD modeling would be a better approach to that, right? The feature scheme is not recommended for high resolution simulations. And when I say high resolution, this is higher than 3 times the rotor diameter. So as rule of thumb, if we consider a 300 meters rotor diameter, 3 times that is 1 kilometer horizontal resolution. That's what is recommended. And the feature scheme seems to be pretty much useful in offshore size, since the horizontal variability is smaller than in onshore. And maps and WRG files at 1 kilometer resolution offer an accurate description of the wind resource. Long-term period is possible, but for wakes analysis, maybe a shorter period of time can do the job already, right? And we will deliver two outputs: the regular WRF parameterization and the feature scheme wakes validated, so you can see the difference. The methodology, as you can see here, there is some information we would need from you before setting up the feature scheme at WRF. It's not just about your wind farm, but when possible, also the surrounding wind farms. This can be either the existing ones, where easy information to have access to, or future wind farms, which is not always that easy to get this information, but we suggest making some assumptions like number of turbines to be installed, the hub height, the rotor diameter, better than doing nothing, I guess. And for the isolated wind farm, feature scheme does not seem to make much sense, right? This is an important message to take home. See this example. This is a 400 square kilometer region with a wind farm south of this area. You can see the mean wind speed maps for the regular simulation at the left-hand side, and feature wake simulation at the right-hand side, that it's going to affect your future wind farm. In this example, shows how the feature scheme decreased the predicted wind speed up to a 13% in the center of your wind farm. To a story, only external wakes recommended, not internal wakes yet, okay? Then last but not least, second customized solution are low resolution grids that some customers use for either early stages of the offshore wind farm development, when you go to tenders and you need to have an idea of the wind resource in a large area, or even for wave analysis in the site. Since waves are created many miles away from your area of interest, then long-term series seems to be a useful tool for that. So again, we can pull out up from 10 years or even 38 years of data. And net CDF files are available. So this has a raw WRF output data for you to calculate. And this is basically what I wanted to talk about today, just wrapping up what we went through, that we have supplied data for most of offshore projects worldwide, that we have standard offshore solutions. And we have extensively validated both internally and externally some of that solutions, but also we can customize anything that you can think of. So request your needs and we'll see what we can do. And finally, you can go to our knowledge center, where you will see a lot of documented data for our offshore, not just offshore, but about all of our products. So last we invite you to come and visit us in May in San Antonio, Texas for the Clean Power 22 edition, where we will have this booth 1633, where we will be glad to attend you and answer any questions you may have. So this is it from my side. Patricia, please, you can share the answers that we just pulled out. So for regions, it looks like it's pretty even, but 50% is still in Europe, but 30% in US and Mexico. I'm surprised about that, but that's good news. Good news. Next one, let's see. The reanalysis, basically Area 5, and depending on the site, surprisingly, no CFSR were selected. That's interesting. And the last about the areas that you are, it seems that less than 1,000 square kilometers is the most common size of your project, which is it's good news for us. This is it. I think we can start with the Q&A. Let me stop sharing my screen right now. Again, apologizes when I got stuck, but we had some issues. Let's see the Q&A. Patricia.
Thank you, David. We have some questions here from some attendees. The first one is asking, can you use the Vortex series in initially assessing the wind resource in the area without any on-site measurement?
Well, that's a tricky question. You can, but maybe you should not. Why? Because, well, it's better having this than nothing, but ideally, Vortex series are for when you have at least a few months of measurements, right? But maybe Paul can add something to that. But the best thing is that you have wind measurements. Then we can complement that.
Yeah, I think this is pretty, I would pretty much say the same. I would focus into the LES probably. If you really don't have any measurements, our best solution in that case would be to use 1 year of LES data, a high resolution simulation for the location, where we, let's say, can warranty a little bit more accuracy than in the series. I mean, the series are typically quite okay as well, because in offshore, still you get a quite nice distribution of the wind speed, even though the resolution of the series is not perfect. Okay, it's a 3-kilometer mesh for the model, but the LES high resolution, both because of the fact that it's modeled at 4 Hz, as David suggested, indicated, and also because the mesh of the model is 100 meters on the horizontal, you will get a much better description of the wind distribution, both regarding the wind rows, the wind, the histogram, variable parameters, etc., and also, of course, the vertical profiles and so on. So the LES would be our recommendation in that case.
Perfect, thank you, Pau and David. There is another one, says for farm near coast, will the larger area covering the coastline, if not supplied to us, also be modeled at 100 by 100 square meters?
Yes. I mean, this is 100 by 100 square kilometers, I guess. It's maybe too large, but what do you think? But yeah, as I explained, we covered the larger areas than you're interested in. But this is a...
Yeah, I as far as I understand it from the question, I think it's quite technical, I would say. So good question. I would say I understand from the question, it's that even though the region that the customer is interested in, it's fully offshore, the area under interest may be near the coast, okay? Maybe let's say a few kilometers away from the coast, but still, let's say that the final region that we will be delivering to the customer is fully offshore. And of course, it will be 100-meter resolution, for example, for the farm product or the blocks, okay? So the WRG files, the wind resource grid files that the customer will typically use at the end, they will be only offshore, but this question is focusing on whether the model is taking into account the coastline also at 100-meter resolution, okay? Even though the coastline is out of the boundaries of the customer, okay? That's what I understand, okay, from the question.
I think so, yeah.
Okay, so so two or three makes it enough to answer it. So so I think the answer is we will take there is a buffer in the model that covers a larger area than the one that is indicated by the customer, and which is the final area that we deliver. Okay, so this buffer area in the model is typically about 20 to 25% of the extension of the so let's say if there is a square of, let's say, 10 by 10 kilometers of the cost of a customer, which is a very small area, okay, but 10 by 10 kilometers of interest, we will be modeling 14 by 14, something like this, still at 100 meter resolution. So that's about 2 kilometers on each side, which is 20% of the final area requested by the customer is still at 100 meter. But still, it could be that this is not even enough to be catching the coastline. Okay, so we need even farther. The coast is even farther away. So that means that the model will really model the coastline, but in this case, it won't be 100 meter. Okay, it will be 300 meter, which is the next nested mesh of the model. Okay, WRF works into a downscaling process. So we go from, let's say, 9 kilometers, then 3 kilometers, then and so on and so on. We finally get the high resolution mesh. So that means that if your wind farm is very, and I will finish the answer, if your farm is very far away, it's quite far away from the coast, the model won't be capturing the coastline at 100 meter, but 300 meter probably. Okay.
Okay, perfect. I think it's very clear. Joseph Flores is asking, have you validated the TI of LES with measured data onshore and offshore project? I think David already answered this during the presentation, but David, if you want to add something.
Yeah, thank you, Josue, for the question. We have this validation documents that you can access in our knowledge center. We have, but unfortunately, sometimes we do not have the standard deviation data to validate the turbulence in those sites. So we can validate the wind speed, but I know that the LES, the strength or the power of the LES is having information, as I mentioned, about the ambient turbulence, which unfortunately it's not always possible to validate. But as soon as we get more data, we will be glad to validate more sites with the turbulence intensity.
Perfect. And the next one, there are two more questions. One is, hello, how the wind shear looks like for offshore projects? Is it near zero?
That's a good question. Pau, I leave that to you because probably you have better figures than me in mind, right? What do you think?
I mean, yeah, that's good. I can answer that, or maybe not, because that absolutely depends on the site. Of course, typically what we are seeing is that in our both in our simulations and also in the measurements, we typically see that in offshore, the vertical profiles usually have a lower shear, especially at higher heights, at high hub heights. Okay, so let's say above 100 meters, then you get profiles that have a lower shear, okay, than in onshore, because of the roughness. Okay, the roughness is very low, so that means that even a typical profile by using the logarithmic profiles will indicate that. Okay, but still in the lower, let's say on the first 100 meters, to say something. Okay, so to say as an example, there are sites in which especially under specific conditions, you know, very cold temperature of the sea surface or very high temperature of some front, or there are certain events in which the vertical profiles in offshore conditions can be very extreme, even with low level jets. Okay, so we inverted vertical profile. So that depends a lot on the site, but typically I would say that yes, as an average for the annual long-term mean wind speed average, the vertical profiles in offshore have a lower shear because of the roughness, right, which is very low.
That's great. And this is the last question in the Q&A section. If someone wants to add something, we still have a bit of time. Do you have any experience by comparing LiDAR measurements and LES TI onshore with conclusions could be extrapolated to offshore?
I would say no, because there's the different terrains, right? Whereas onshore, you can have flat terrains and complex terrains or semi-complex. Whereas if you go offshore, then that's totally different. You have just, since we do not have any wave modeling, as I explained at the beginning of my presentation, you could see like the offshore side is like a basketball court. So it's like, it's all flat, but I would not extrapolate the conclusions from onshore LES turbulence intensity to offshore. But Pau, I don't think. Well, what do you think about that?
Yeah, I think I completely agree with this. And I think the question even goes a little bit further, because it's explicitly mentioning if the comparison has ever been made between LiDAR data and onshore simulations. So not just whether our MetMast validations onshore can be extrapolated to offshore, which I agree with you, David, that it's completely, you cannot do that, right? It's pretty similar to the fact that you can typically simulate a flat terrain with some grass, and results are quite okay, but then you go into a forest, it's completely different, okay? It's also onshore, but the model performs different, okay? So, but in this case, even the comparison with LiDAR, I have to say that at Vortex, all the validations that we've been making, we've been running for the last years, and which are available in the Knowledge Center, they have been made against MetMasts, not LiDARs, not just for both in onshore or offshore. So let's say that we cannot extrapolate this because we don't have the comparison really, right? So.
Perfect. And Rupert Crichton is asking you, Pau, are those high turbulence events predictable? The ones you were referring in the question before? Yeah.
I have to say that we've been running nice calculations in offshore, both for the and in this case I have to refer to time product domains. So time domain products available at Vortex, okay, which would be the LES and the blocks, okay? Both calculations, even though in the blocks we don't deliver explicitly the turbulence, still we can do some analysis internally to check whether the model is correctly working in relation especially to vertical shear, which is pretty related to the turbulence events. And both in the LES and the blocks, which are products where we have information on time, so we can study specific events during nighttime, winter, and cold events, for example, so very specific events. Yes, we've been detecting nice low-level jets and extreme shear or veer of the direction. And so yes, they are predictable. Of course, the prediction that we do is not perfect, but still over 1 year period, for example, we've been detecting really nice vertical profile changes of the model, which are in accordance with measurements. So of course, there is some correlation and some metrics that try to capture this ability, the accuracy of the model on these aspects. But yes, the model is responsive to this. So a simulation in the north of Finland, offshore, south of Finland, probably it will be very different than in the east coast of the US, where the relationship between the sea surface temperature and the air temperature are completely different. And that creates stability conditions that depend a lot on the season of the year or the month or the day of the year. Okay, so, and the model really predicts that.
Okay, great. There is no more questions for today. I don't know if someone wants to add something. We still have 4 minutes, 5 minutes, if someone wants to ask something to Pau or David. Otherwise, we will finish the webinar here. And I will send you in the next days the presentation and also this recording, and I will add some documents that David talked about it, the validation for offshore and some other external validations for you to have. And that's it from our side. So thank you very much, all of you, for attending today's webinar. And if you have further questions, please write us an email or write an email to David, and we will be very happy to help you.
Just to finish, thanks. I want to say thank you again to not only the people who attended the webinar, but also you, Patricia and Pau, because you're based in Barcelona. It's 5 p.m. in the evening for you guys, and we really appreciate the effort and the support that you are giving from our headquarters in Barcelona. Thank you so much, and see you all soon.
Thank you. Bye.
Thank you. Bye-bye.